Hello everyone, welcome back to the channel. So today we are going to look at another property of perfect squares, that is when n is a perfect square of a positive integer, then n is congruent to a0 mod 10. So basically a0 is the last digit of n, then so last digit of n is a0, then a0 can only belong to this set. So that means a0 can be either one of these values. So it can only be 0, 1, 4, 5, 6 or 9, nothing else. If it's something else, then n is not a perfect square. So we will formally prove this, and as usual, we can start with some real examples of perfect squares to understand the problem first. So n is the set of perfect squares, and I've done something like this in the other video on perfect squares. So n will belong to the set of perfect squares, and I will try to link that video in the description. So this is a countably infinite set, and where the set contains all the perfect squares that are positive integers. So to focus on the property we are trying to prove here is to define out the last digit. When you divide something by 10 and look at the remainder, you will always get the last digit in a decimal number representation. So 1 is congruent to 1 mod 10. Now once again, writing mod 10 on the right hand side is a more conventional way of doing it. I had in another video I had shown it on the left side. But the idea is the same. So 4 mod 10 is 4. I'm looking at perfect squares. 9 when divided by 10 leaves a remainder of 9. 16 when divided by 10, 10 plus 6, so leaves a remainder of 6. And 25 when divided by 10, 25 is congruent to 5 mod 10. So you can see that these values on the right hand side are basically a0. These are a0 values. And we can see that 1, 4, 9, 6 and 5 all belong to this set. So that's what we are about to prove, not just for a limited set of numbers, but for the whole set of perfect squares of positive integers. So I'm going to rub this off, create some space. And to begin with, as I've done in the other video, I'll define something like n is equals k squared, and where k is a positive integer, we'll write it as k is a positive integer because if n is a perfect square and a positive integer, its root has to be a positive integer as well. You can denote it as something like this: square root k square root of n. We have talked about this, and here I will need a slightly different approach than what I had when I was dividing by 4. Here I'll need to focus on the last digit, so I'll have to think about the digits of n. So before thinking about n, I can think about k, just like we've done before. So if k is represented as a j plus 1 digit number, basically it's a positive integer, again another variable j, but I'm representing here k, not n. So j will also belong to the set of positive integers because it's the number of digits in k. So, or rather, positive integers union 0, because if k is a one digit number, then j is 0. And then k can be written as a number like this, a number that looks like this, all the way up to a1, a0, where ai's are the digits of k. Uh, to visualize this might be slightly confusing. This is more of a formal representation because I need to prove something, but I can take examples of k. So let's say k is a 4-digit number and k equals 9876. Now this is just an example to explain the notation, nothing to do with the proof. So 4-digit number, so j plus 1-digit number, k was a j plus 1-digit number, so j plus 1 is 4, then j is 3. If j is 3, then I would represent k as, I'll start with aj, so I'll start with j equals 3, a3, a2, a1, and a0. That is k. So a3 equals 9, a2 equals 8, a1 equals 7, and a0 equals 6. Just to explain the notation of how I'm representing k with an example, of course. And you can verify that while this is the representation, if I had to write it as an identity, I would write k equals 10 raised to the power 3 times a3 plus, this is the basic property of a number system, and this number is in the decimal system. So this is a standard representation, and I'm trying to explain it with a simplified example, but because we will need this representation for the proof. So plugging in the values of ai's, the digits of k, those were 9, and a2 was 8, and a1 was 7, and 10 raised to power 0 is 1, so a0 was 6, 1 6. So as we can see that this is 9000 plus 800 plus 70 plus 6. This will give us back the number k, 9876. All of this is to explain the representation of k with this real example and how we represent a general decimal number in the decimal system that has a base of 10. Now why am I doing all of this? To segregate the last digit, to, to write k in terms of the last digit somehow, because if you see a0 here, this is the last digit, 6 is the last digit, 6 is the last digit of k, and somehow I'm interested in last digits in my proof, so hence this approach. But still some way to go here. A more generic A where I don't know J or K, or rather I don't want to specify them to a particular value because I want a generic proof. So in that case K would be, if K is represented as this, K would be 10 raised to J Aj plus 10 raised to power J minus 1 Aj minus 1 plus, I'll put dots because I don't really know how many digits are there. This is a generic number plus a0. I'm not writing 10 to the power 0 here. That's 1. So this is a representation of j, and I'm gonna need this representation of k to go back to n and find something about n. But firstly, we can find something from here, something interesting, and that is every term here is multiplied by 10. Every digit here is multiplied by 10 except a0. So I say that if k is congruent to a0 mod 10, can I say this? Of course I can say this. Everything else has 10, so 10 will divide everything and leave a remainder of a0. So that is this. Basically what I'm saying is that k leaves its last digit when it's divided by 10, and that's the whole definition of a last digit. That's expected, right? So in this particular example, the last digit is 6. K will leave a remainder of 6 when divided by 10. This is known fact. This is completely known. But I just wanted to point this out for k, because later I'll have to find something similar for n to prove this. So now, since I do have a representation for k that's like this, I'm gonna go ahead and plug this into n. So n was k squared. So n is k into k. I would rather rub the whole part off because I need some space for n. So k times k. Then I had a representation for k before that I rubbed off, and that was 10 raised to the power j aj plus 10 raised to the power j minus 1 aj minus 1. Now, I'm doing all of this because this representation has tens and I need something in the form of 10. That is to explain why we are using this approach. This is multiplied by itself because whatever you have inside the bracket is just k. And we don't really know j or k. That's the whole point of a generic proof. You're proving an identity, so it has to be generic. N is this whole expression multiplied by this. It's the same k to k, but two terms is in the bracket. Now, if I try to expand whatever is inside the bracket with the laws of distribution, with the distributive law of algebra, then I'm gonna have to take one term from this and multiply that with all of the terms here. Let's see what I get. So this first term multiplied by this first term is 10 raised to the power j aj squared plus this term multiplied with the second term of this expression, that is 10 raised to the power j into j minus 1. I'll get some more terms here because I have the dots. And then if I multiply this with the last one thing here, that is 10 to the power j plus 1, j plus 1 10, then aj a1 plus this multiplied with the last one, 10j aj a0. That's just the first term multiplied with everything inside the bracket. I have to do it for the other terms as well. So this is the first term. For now, if I look at the second term, I will get this multiplied by the first one. So 10 j minus 1 aj minus 1 plus second term with second term, then probably the same thing here. J looks like I, sorry. So second with second is j minus 1 squared aj minus 1 squared plus, again a lot of dots, then this multiplied with the second last term, that is j minus 1, and I have a 10 here, so it's 10 raised to power j aj minus 1 into a1 plus this multiplied with the last term, it's 10j to the power minus 1 aj minus 1 is 0. I don't know all the terms, so I cannot just keep on doing this. I'll have to use dots for the other terms, and a lot of dots. After a lot of dots, I'm gonna have the second last term here multiplied with everything here. So this will be 10 raised to j plus 1 aj a1, second last term with the second term, 10 raised to j aj minus 1 a1 plus more dots, 10 squared a1 squared plus second last term with the last term, 10 times, don't have space, okay, plus 10 a1 is 0. So don't mind the writing there. Then I'm going to do it for the last term. Interesting thing as I keep on distributing these brackets is that everything has 10 here. Because everything had 10 in the representation of k, everything had 10 except a0. So the 10s are multiplied among themselves to give more 10s. It's never going to be less because there's no division, there's only multiplication. So the terms having 10s multiplied with each other gives you more 10s. And that's a very important observation in this proof. So when I multiply the first term here with this whole bracket, I got 10s everywhere and more 10s than this one had, except only when I multiplied with a0. a0 didn't add any 10, so I got 10 to the power j. So we are never subtracting 10s, we are just adding the powers of 10s. Not subtracting the powers of 10s, only adding the powers of 10s in this multiplication. Because multiplication only adds powers. So everything has 10, everything has 10 even here. So this one was multiplied with a0, but the second last term here had a 10, so that 10 is still here. So we can intuitively feel that a0 might be the only term that doesn't have a 10, and we need that. We need something that doesn't have a 10 because we are about to divide by 10. So a0 multiplied by the whole thing again, this might look like a really long, but this is kind of a solid way of proving it. So we're gonna get these terms. Again, I get 10s everywhere because even though a0 doesn't have a 10, everything here has a 10. Even this one, it has a 10. a1, a0. Only the last term here, only the last term of this second expression doesn't have a 10. And I was multiplying with a0, that also doesn't have a 10. So I only get an a0, a0 squared term that doesn't have a 10. Everything else in the representation of n as a summation of digits, combinations of digits, has 10s except only a0 squared. So that's the magic of this proof, and this expansion works the magic and tells me that, hey, this number can just be represented as 10 multiplied by something, some positive integer, because I don't only have digits, so I'll get a positive integer plus a0 square. How about I write n like this? I can write like this because everything has a 10 except a0 squared. But yeah, that's good to know, but I'll directly write the observation from here, and that's n equals k squared is what I expanded for such a long time is congruent to a0 squared mod 10, where a0 is the last digit of k, but I was initially supposed to prove this for the last digit of n. So this is kind of a relation between the last digit of n and k when there's a mod 10, but I still have to go back to this somehow, and I get an a squared here, a0 squared, and a0 according to my representation is the last digit of k. So I'll just keep this identity that I will need, and we'll finish off with all the possible values of a0. So a0 is the last digit of k. Since it's a digit, that is, in the decimal system it's a digit, so it can only be an integer between 0 to 9. So a0 has to belong to this set. And also intuitively you know that you're dividing, like a0 is just k is congruent to a0 mod 10. A0 is the last digit of k, so it has to be something between 0 and 9. So I'll tabulate all possibilities of a0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And I will write a squared 0, 1, 4, 9, 16, 25. Hey, this is probably the only part in the proof where we're actually squaring things, because, but you might have said we started off with squares, so we would have a lot to do with squares, but we did more with decimal number systems and the representation. This is the first part where we are squaring things, and you might feel that since the problem is in terms of square, you will have to square at some point in the proof. So when a0 squared is less than 10, then the last digit of k and the last digit of n become same, because the last digit of k is a0, and if since n was something, I wrote this earlier, n was something of this form, so this m gets multiplied by 10 and it doesn't contribute to the last digit, only a squared contributes to the last digit. So n was congruent to a squared mod 10. This means that when a squared is less than 10, n will be directly a squared. So directly congruent to a squared mod 10, that means this is the last digits of k, this is also the last digit of n, last digit of n, last digit of n, last digit of n. Only when a0 squared happens to be greater than 10, we have a 16 here. So what we're going to have to do is, now n will be when a0 is a0 squared is 16, n is basically 16, congruent to 16 mod 10. These kind of representations when a0 is greater than 10, we are just going to have to divide by 16 by 10 and write the remainder. So this is simply mod 10. So that way this will be 6 mod 10. So the last digit of n is 6. This will be 5 mod 10. Last digit of n is 5. This would be 6 mod 10. The last digit of n is 6. This will be 9 mod 10. The last digit of n is 9. This would be 4 mod 10. The last digit of n is 4. This would be 1 mod 10. The last digit of n is 1. And there you go. I have a list of all possible last digits of n. That's what I had initially set out to prove, and that can be 0, 1, 4, 9, 6, 5. Yeah, I already considered all of them. These 6 possibilities, these are the possible last digits, and you can prove that it belongs to this set. In other words, any perfect square of a positive integer can have a last digit out of only these 6 possibilities. Why this is such an interesting property is, if you're ever told that, hey, n is a perfect square of a positive integer that only consists of n only consists of 6, sorry, not 6, n only consists of something that's not within this set, n only consists of 2's and 3's. Only 2's and 3's can be the digits of n. So can n be a perfect square? If n is a positive integer, no, this is a question, sorry. If n is a positive integer that only contains 2 and 3 as its digits, can n be a perfect square? The answer is obviously no, because if 2 and 3 are the only allowed last digits of n, only allowed all digits of n, then the last digit has to be either 2 or 3. And the last digit of a perfect square cannot be 2 or 3. So this number will never be a perfect square, a positive integer where the digits are only 2 or 3. And we can find such interesting proofs. These are the kind of problems where this can be applied and can be useful. So thank you so much for staying with me, and thank you so much for watching this.